Swayam Prabha. Digital India. Educated India.
Students, hello. Welcome to week 2 of CS 747. So you will remember last week we got started with the topic of bandits, stochastic multi-arm bandits, and that's what we will continue with this week. So here is a organization of this week's lecture in 5 parts. So remember last week we defined what was a stochastic multi-arm bandit. We defined the notion of an algorithm. And thereafter, we said what we would like to minimize is regret. Okay, so an algorithm will incur a certain regret over a horizon on a given bandit instance. We would like algorithms that achieve small amount of regret, preferably sublinear regret. Okay, which means if you take the ratio of regret and horizon, as the horizon becomes larger and larger, that ratio goes to 0. And that's what we will start out with. I think, left you last time with the question, do the epsilon greedy algorithms 1, 2, and 3 achieve sublinear regret? Okay, so we will actually begin by answering that question. Thereafter, we will ask, what is the best we can hope to achieve in terms of regret? Clearly, we must incur some regret in general if we want to learn and perform well on a bandit instance. Right? Because we don't have the knowledge of what's the right arm to play on any bandit instance. It's only understandable we should incur some regret, but what is the lowest that we can incur, right? So that is the second part of the lecture. We will have a lower bound on the regret that is discussed. Thereafter, we will look at some nice algorithms that happen to do substantially better than the epsilon greedy algorithms we saw in class last week. So these algorithms are the UCB family of algorithms, and thereafter the Thompson family, the Thompson sampling family of algorithms for bandits. Finally, we will just summarize and conclude. Okay, so let us go back to the question of regret, right, and see how we can achieve sublinear regret, if at all we can. We can. Let's begin with these 2 algorithms, epsilon greedy 1 and 2, which we called, together you can think of them as epsilon first algorithms, which for the first epsilon t pulls, they pull uniformly at random. Thereafter, they start exploiting. Okay, there is a little bit of a difference between epsilon greedy 1 and 2, but both of them more or less are exploring first and then exploiting. Now, remember the graph we drew towards the end of last class. I'm drawing the same x and y axes. On the x-axis is the number of pulls, and on the y-axis is the expected reward at any particular time step. And remember that the area between the red line and the P star line is the regret. So looking at this graph, we can ask the question, will this regret as a ratio of t go to 0, right? So here is how the graph is going to look for epsilon first algorithms. For the first epsilon t pulls, right, we are picking arms uniformly at random, and therefore the expected reward that we're going to get is p average. Okay. Thereafter, after having explored, we'll start exploiting. Now it is conceivable that we'll be pulling a good arm, right? Maybe an optimal arm. So it's quite possible that in the exploitation phase we do better, maybe as well as P star sometimes, maybe slightly worse off sometimes, really depending on the outcome of what happened during exploration, right? But the point is, whatever we manage to do in the second phase, right, even if we concede that we are doing, let's say, optimally playing P star in the exploitation phase, it remains that we have an exploration phase whose length is epsilon times t. Right? So if you ask the question, if you ran this algorithm for a horizon of 2 times t, right, rather than t, then how is this graph going to look like? So the graph is going to look pretty much the same. Instead of t over here, you will have 2 times t, and this number, crucially, is going to be 2 times epsilon t, right? So the ratio of this small rectangle here, right, between p average and p star for epsilon t steps, that rectangle is just going to get stretched if you stretch the horizon, okay? And so the ratio of this to t is going to be essentially epsilon, okay? It's going to be at least epsilon. It might be a little bit more if we add the area from here, but it's not going to go below epsilon. Okay, that's because whatever you make t, if you make t to be x times t, right, the number of exploration steps is going to be x times epsilon t, right? So the ratio of the regret to horizon is going to remain at least a constant. So let's look at a small mathematical working to establish this. So one step at a time. So during the course of this lecture, in fact, the entire course, we will have a few of these mathematical derivations. Most of these, right, you will not need any extra results. Whenever we need any extra results, I will sort of convey them to you up front. But you should be able to follow this line by line. Okay, so we start out by looking at the regret. Okay, and finally we are going to establish that regret is a linear function of t. Okay, it is lower bounded by a linear function of t, which is what we mean by saying it is omega of t. How do we do this? So the definition of regret is it is t times p star minus what the algorithm actually achieved in expectation over t steps. Now this second term I'm going to split. Okay, it's a sum over t terms. I'm going to just look at the first epsilon t terms and then the remaining t minus epsilon t terms. Okay, I'm just splitting up the sum into two separate things, and we will look at these two things separately. So the first term I'm just carrying over. Now the second term, we know exactly what it is. If you're doing uniform random sampling for the first epsilon t steps, the reward that you're going to get is going to be epsilon t times p average, right? So this is an exact equality. I've not changed the last summation. Now the last summation is a sum of rewards going from epsilon t through t minus 1. Let us be generous and allow this to be as high as possible, okay? Because we're looking for a bound, right? A lower bound. It's okay for us to give sort of extra credit to the algorithm. So even if the algorithm does not actually latch on to an optimal arm, right? Let's act as though it did. And therefore, let us say that this number, right, is going to be at most t minus epsilon t. That's the number of pulls times p star. Okay, so the actual sum, right, at most it can be that number times p star. Because we have a minus over here, we say that it is at least, right? There's a greater than or equal to with the accompanying term here. Now you rearrange terms, cancel out a little bit, and what you find is that this amounts to be epsilon times p star minus p average times t. Okay, and this is a linear function of t, right? P star minus p average in general is going to be a positive quantity. Epsilon is a positive quantity multiplying out t. So even if these numbers are very small, even it's going to be 0.0001 t, that's a linear function of t. Okay, and so this ratio is not going to go to 0. It's going to go to whatever that number is. Okay, so the intuitive idea here is that epsilon first, in the first epsilon fraction of pulls, it has already incurred sublinear regret. Okay, it can't do better than sublinear regret because of the exploration phase that is there at the beginning of the algorithm. Okay, now let's look at the second family of algorithms, which was epsilon greedy. Okay, which is like at every step with probability epsilon doing uniform random sampling, and with probability 1 minus epsilon, it's exploiting, right? So if we draw the graph for epsilon greedy, here's how it's going to look. Now, depending on your implementation, it might start at p average or start somewhere else, but this is just like a rough placeholder. Now, the important point is that even if this graph explores the arms sufficiently often, right, and it has figured out that this is the order of the means, right, because let's say it has sampled each arm a very, very large number of times, and at some point the order of the empirical means is consistent with the order of the true means, let us say. Even so, the algorithm chooses to explore with probability epsilon. Okay, it's not going to sort of make full use of its knowledge. It continues to explore with this probability epsilon forever, right? So therefore, wherever we see this graph, right, at any point of time, we have the assurance that the reward that is achieved by the algorithm cannot exceed p star times 1 minus epsilon. That's maybe the exploitation probability. Sorry, that's probably the expected reward from exploitation, right? Which is 1 minus epsilon times P star. That's the most you can get. But there is this epsilon times P average, right? The probability epsilon, you are sampling uniformly at random, and those fraction of pulls are going to give you reward of P average, which is smaller than P star. So this number is smaller than P star. So because the algorithm can never breach this dotted line, right? The regret that it is going to incur is lower bounded by at least this difference, right? Times T. And this difference is a positive quantity, and therefore this is also going to have a linear regret. Okay, so epsilon expected value of reward, right, can never exceed P star times 1 minus epsilon plus epsilon times P average, as I have indicated on the graph. So how does the math work out for this case? Again, the regret is just write out the definition. It is T times P star minus the sum of the expected rewards. Now this time, instead of splitting the sum into two sums, we will split each term in the sum into two things, right? What's happening inside each term is with probability epsilon, you're getting exactly P average in expectation. And the remaining probability, you might be getting any reward, right? Let's again be generous and say that the algorithm is actually getting P star reward. That's the most that it can get. Even so, right, if we find what this quantity now amounts to, it's basically the same as last time, right? It's epsilon times P star minus P average times T, okay? And that is again linear in T. So both epsilon greedy 1 and 2 as well as 3, right? Which means both epsilon first and epsilon greedy strategies are incurring linear regret. I mean, these are not very bad algorithms, right? Because in practice, right, if you have a horizon of 1,000 pulls and you tune epsilon reasonably well, you might do reasonably well. But from a mathematical point of view, right, from the notion that you should get sublinear regret, right, as T goes to infinity, that is not satisfied by either of these algorithms for different reasons. The epsilon first algorithms give away a small fraction of the regret right at the beginning. Epsilon greedy algorithm continues to give it forever. Okay, so both of these algorithms are not satisfactory. The question is, can we do something about this, right? Can we somehow make a change to these algorithms and achieve sublinear regret? In general, right, if algorithms have to achieve sublinear regret, what properties must they have? So we will answer both these questions. We will start by looking at a somewhat abstract notion of what algorithms need to satisfy in order to achieve sublinear regret. So I'm going to say it roughly without too much mathematical rigor on this slide. Okay, I have a more formal definition on the course webpage. You can look at that if you're interested. But I'm just going to give you the intuition over here. So in order to achieve sublinear regret, an algorithm must meet two conditions. Okay, so let's call these conditions C1 and C2. C1 is the condition of infinite exploration. Okay, what does it mean? It means if you take the limit as t goes to infinity, okay, each arm in the bandit instance must be pulled an infinite number of times. Okay, so it should not be that the algorithm runs forever, but some arm in the bandit has been sampled only 10 times or even 10 million times, right? As long as it's a finite number, that's not good enough for the theory. And C1 is the condition that as you make time longer and longer and longer, you're guaranteed that each arm will get pulled more and more and more times, right? An infinite number of times in the limit. Okay, so let me give you some intuition as to why we need this condition. Okay, so suppose on the other hand, there is a particular arm that got pulled only a finite number of times. Okay, let capital U be some finite number. It might be 10 or it might be 23,000 or it might be 10 million, but it's a finite number. Okay, it's not infinity. So if let's say each arm is pulled only U times, there is a small positive probability, okay, that an optimal arm in the bandit instance actually gave us very misleading rewards. Okay, in fact, with probability 1 minus p star raised to the u, right, an optimal arm, an arm with mean p star, will actually give us only 0 rewards, right? On each pull, it's going to give us 0 reward with probability 1 minus p star. So exponentiate that to u. And that is a probability with which it would have only given us zeros. The crucial point is that this probability, even if it is small is not zero. Okay, it's a finite quantity, and therefore, if after that stage you're never going to pull that arm, right? You will not, right? Because if you're only exploiting, maybe some other arm has at least one positive reward, and therefore you will never go back to this arm, right? Which has only given you zeros. So that's what you end up doing. Then you're going to incur a linear regret, right, as t goes to infinity. Okay, so because of this sort of explanation, right, you can see that it never suffices to pull any arm only a finite number of times, because in any finite number of times, there is a small chance that luck just misled you, right? That arm got unlucky and only gave you very low rewards or zero rewards, and thereafter it's never going to get pulled. So that's not okay. This will not happen if you do an infinite amount of exploration. So that is necessary. So this is condition C1. What's condition C2? So condition C2 is that not only are you exploring enough, you need to exploit sufficiently often. So the formal way of saying that is that the number of times you exploit, okay, the fraction of that over horizon, that number must go to 1. Okay, so let me just rephrase this. So for horizon t, let exploit of t denote the number of pulls up to time t which are greedy with respect to the empirical mean. Okay, so although we sort of use the terms explore and exploit informally when we were talking about the epsilon greedy algorithms, think of a formal definition of the term exploiting at any particular step. So I'm saying on a particular pull you are exploiting if the arm you are pulling, right, is one of the arms with the highest empirical mean. And let the number of such pulls up to horizon capital T be exploit of capital T. So what we need is that the expectation of exploit of T divided by T, right? That number, as we take the limit of T to infinity, goes to 1, which basically means in the limit, right, the fraction of pulls on which you have exploited is basically 1. And therefore, the fraction of pulls on which you have not exploited is going to 0, okay, as T goes to infinity. So here is what we can say, okay? We have these conditions C1, infinite exploration, and C2 being greedy in the limit. Together, right, we can actually make a claim about these two conditions and algorithms that satisfy these two conditions. So let I bar, okay, so this I is written in a sort of funny way, it's called the calligraphic I. Let I bar be the set of all bandit instances whose means, okay, whose true rewards are, let's say, strictly less than 1. Okay, for a technical reason, we cannot include bandit instances who give us the reward of exactly 1. So because these are Bernoullis, right, having a mean of 1 means you'll only get 1 rewards, right? You'll never get a 0 reward. So that introduces a little bit of issue here, which we don't need to get into. But I bar is basically almost the set of all bandit instances that we are interested in. And the result is that an algorithm L, okay, remember that an algorithm is a mapping from the set of histories to the set of arms or the set of probability distributions over arms, doesn't matter. An algorithm L will achieve sublinear regret on all instances in I bar if and only if it satisfies both C1 and C2 on all instances I in I bar. Okay, so what does this mean? If you want to get sublinear regret on every bandit instance, then you need to do an infinite amount of exploration and be greedy in the limit on every bandit instance. The other way around, if you satisfy these two conditions, being greedy in the limit and doing infinite exploration on every bandit instance, then you will get sublinear regret on every bandit instance. Okay, so it's an if and only if, and a sort of quick shorthand for remembering these two conditions, right? C1 and C2. These are called the GLIE conditions. Okay, being greedy in the limit and performing an infinite amount of exploration, and this is basically equivalent to achieving sublinear regret. Okay, so now take a minute and think about epsilon first and epsilon greedy algorithms that we saw, right? Were these algorithms being greedy in the limit? Were they doing an infinite amount of exploration? Because we know that if they did both, then they should get sublinear regret, right? But then we just started out this lecture by saying they don't get sublinear regret. So why don't they get sublinear regret? So think about it. You'll notice that both algorithms do perform an infinite amount of exploration. No, they don't. Well, they do, right? Both of them perform an infinite amount of exploration, but neither of them is greedy in the limit, okay? Because epsilon first algorithms give an epsilon fraction away without being exploiting, whereas epsilon greedy algorithms do it, they give like an epsilon fraction at every step, okay? So neither of them is greedy in the limit, and that's the reason neither of them was able to get sublinear regret. Okay, good. So are we going to just leave them at that, right? Can we go back and make some small changes to these epsilon greedy algorithms to make them sublinear regret, to make them GLIE so that they can get sublinear regret? By all means we can. Okay, so let's look at epsilon first algorithms to start with. These are the epsilon greedy 1 and epsilon greedy 2, right, that we did. So here's the small change we make. Instead of having an exploratory phase that was of length epsilon times t, where epsilon was a constant, let us set epsilon as a function of t, right? So let us explore for epsilon t times t pulls, where epsilon t, right, epsilon subscript capital T, which is the horizon. So let that number be 1 over square root t, for example. It could also be other things, but 1 over square root t suffices, okay? So what this means is that we will do uniform random sampling for square root of t pulls, okay? And thereafter, for the remaining t minus square root t pulls, we will exploit, okay? Will this algorithm satisfy the GLIE conditions? Well, you can see that it's going to explore infinitely often in the limit, right? Because the number of exploratory pulls is square root t divided by n, right, for each arm, and that goes to infinity as the as t goes to infinity. But it's also going to be greedy in the limit because the fraction, right, the number of exploit pulls, which is t minus square root of t divided by capital T, that number is going to go to 1 as you take the limit of t going to 1. Okay, so in the initial step, when you're pulling uniformly at random, even there sometimes, right, you might get lucky and you might have an exploit, right, because you are pulling the arm with the highest empirical mean. But even not counting that, remember that in the second phase, right, we are being greedy with respect to the empirical mean. Okay, at least in epsilon greedy 2, I think that's exactly what we were doing. So you're guaranteed at least so many exploit pulls as a function of t, and that, as you take the limit of t going to infinity, becomes 1. Okay, so it suffices to show that the algorithm is GL and IE. By what we said on the previous slide, it implies that it's going to get sublinear regret. How can we fix epsilon greedy, right, which was exploring with probability epsilon and exploiting with probability 1 minus epsilon? Again, let us make epsilon a function of t. Okay, so in this case, it suffices for us to make epsilon a function of the current number of pulls. Okay, we don't need to know the horizon. So if t is the little t is the number of pulls, let us set epsilon to be 1 over t plus 1. Okay, this choice is somewhat crucial. There might be other choices, but you don't have too much freedom in what you set epsilon t to be. Okay, so a rough rule of thumb is that epsilon t needs to decrease with time, but there's multiple functions that decrease with time, right? Some of them will work, some of them will not work. So we'll get to that. But the algorithm itself is this. Okay, with probability epsilon t, you pull arms uniformly at random. With the remaining probability, with probability 1 minus epsilon t, you exploit. Okay, which means take an arm that has the highest empirical mean and you pull that arm. So will this satisfy the GLIE conditions? It will. Okay, so C1 is satisfied, right? Remember that C1 is infinite exploration. C1 is satisfied because with probability 1 over t plus 1, on every step you are sampling, you are operating uniformly at random, right? So if you see for each arm, it is guaranteed that with probability at least 1 over n of 1 over t plus 1, it's going to get a pull. Okay, of course this is an expectation, but that's okay, right? And therefore, if you look at the expected number of pulls of each arm, that number must be at least the sum of this 1 over n times t plus 1, as t is varied from 0 through capital T minus 1, right? The total number of pulls. And crucially, this function 1 over t plus 1 is such that if you integrate it, right, or if you sum it up like this, you're going to get log t. Okay, this is the harmonic sum. It's going to be theta of log t. Maybe like there's a sort of small constant associated, but nevertheless, each arm is going to get at least theta of log t divided by n pulls with high probability. Okay, and this number as t goes to infinity goes to infinity. So log t is a slow growing function, but it will still go to infinity as t goes to infinity. Okay, so C1 is satisfied. Similarly, C2 is also satisfied because the number of exploit pulls is now t minus theta of log t divided by capital T. Okay, and that number will go to 1. Okay, which is what we need. When we took a constant epsilon, right? When we took not epsilon as a function of t, but as a constant epsilon, what happened? What went wrong with epsilon greedy, right? What went wrong is that over here, right, the fraction of exploit pulls was no longer t minus theta of log t. It would have been t minus some constant times epsilon t. Okay, so it would have been linear in t rather than log t over here. Therefore, we were not satisfying condition C2. Question for you to think about: what would happen if we took epsilon t to be 1 over t plus 1 the whole squared? Okay, instead of just 1 over t plus 1. So what you need to think about is if you sum up 1 over t plus 1 the whole squared over here over time, right? Will that also give us a function that is growing with the horizon, or will it not? So that's for you to figure out. The other thing that you can do with many of these, what we see on these slides, is you can write a small program and implement and see what happens. Okay. In fact, you'll see a difference between epsilon t greedy with 1 over t plus 1 and 1 over t plus 1 the whole square if you write a program and do it. So I encourage you to do that as well. Okay, good. So I hope you have built some familiarity with the notion of achieving sublinear regret. Next comes the question for us. Sublinear is good. Okay, now we know that we have algorithms that do achieve sublinear regret, but sublinear means so many things, right? So square root of t is sublinear, log t is sublinear, log t is sublinear. What is really the best that we can do in terms of regret? Can we get log t regret? That would be great, right? Because log t is a function that grows very slowly with t. It grows much more slowly compared to, let's say, square root of t, which is a polynomial function of t. So what's coming up next is a discussion on what is the best we can hope to achieve with an algorithm. Okay, so let's look at this lower bound. Now, we have to be a little careful in terms of how we ask this question. Okay, what's the least regret you can get? Suppose I ask you this question. If you think about it, you can actually get zero regret sometimes. Okay, so imagine that you have an algorithm that is always pulling arm 3 in a bandit instance. Okay, now suppose it is running on a bandit instance in which 3 is the optimal arm, right? It's going to get zero regret on that particular bandit instance, right? So without giving sort of more constraints, we have like a trivial answer saying we can get zero regret, right? But the point is that same algorithm that gives you zero regret on some bandit instances is going to give you linear regret on other bandit instances, right? So suppose there's a bandit instance on which 3 is not an optimal arm, right? Maybe 5 is the optimal arm. If you're always pulling 3, then you are not doing anything meaningful. You're just going to incur linear regret, right? So that's not okay either. Okay, so an algorithm that always pulls the same arm is a good example of an algorithm that is good on some instances but not good on other instances. What we would desire, right, is an algorithm that does well on every bandit instance. Okay, we wanted to actually learn about the bandit instance by pulling arms in that bandit instance and still doing well, right? So if we want that sort of a characterization, there is a classical result that we can invoke. This is called the lower bound of Lai and Robbins. Okay, this is from 1985. Okay, it's 35 years old, and the statement is in two parts. Okay, understandably. So here's the first part of the statement. Okay, so let capital L be an algorithm which has the property that for every bandit instance, okay, in I bar. Okay, remember that I bar was the set of all Bernoulli bandit instances with means between 0 and 1 excluded. Okay, you can't have exact 1. But it's for simplicity, just think of it as the entire family of bandit instances. let L be an algorithm such that for every bandit instance in I bar and for every alpha greater than 0. Okay, so alpha is just a small number. It's a scalar value. Okay, but for every alpha greater than 0, as the horizon t goes to infinity, this algorithm has the property that the regret at horizon t of L, this algorithm on instance I, is little o of t to the alpha. Okay, so little o of t to the alpha means if you do regret divided by t to the alpha and take the limit of t going to infinity, that goes to 0. Okay, this is the notation used in algorithms. Okay, a function is f is little o of g if you do f divided by g and take the limit, right, of the parameter, that goes to 0. So again, let L be an algorithm such that for every bandit instance in I bar and every alpha greater than 0, its regret, right, is little o of t to the alpha. Okay, now simpler, maybe qualitative way of saying this is L is an algorithm that on every bandit instance in I bar achieves what is called sub-polynomial regret. Okay, t to the alpha for whatever alpha you take. Alpha equal to 1, alpha equal to 0.5, alpha equal to 0.0001. These are all polynomials in t. Okay, and you're doing better than that means you are doing sub-polynomial. Okay, so L is an algorithm that gives us sub-polynomial regret on every bandit instance in I bar. Suppose. Okay, now comes the second part of the statement, which says then for every instance, bandit instance in I bar, as t goes to infinity, the following statement is true. Okay, if you take the ratio of regret to log of t, okay, this is let's say the natural log of t. That number is bounded by this big quantity here on the right hand side. It suffices for you to just think of this constant, this number here as a constant. Okay, in fact, it is a constant. Let's maybe look at what it is. So we are doing a sum over all the arms in the bandit instance, which are suboptimal arms. So we are looking at every arm A for which PA in that bandit instance I is not equal to P star, right? Which means it is smaller than P star. For each such arm, we are taking a term. So that term is P star of P star minus PA. Okay, that's the difference between that arm's mean and the optimal mean, divided by KL divergence PA of I and P star of I. Okay, so maybe let's just get that out of the way. So KL divergence is a way of measuring the difference between two distributions. Okay, so here for simplicity we are assuming these are Bernoulli distributions, and so the KL divergence between Bernoulli distributions with means, let's say x and y, right, that's defined to be x log x over y plus 1 minus x log 1 minus x over 1 minus y. Okay, you need to be a little bit more careful in the definition. For example, if you run into 0 log 0, you have to define that to be 0, etc. But let's not worry about the corner cases. What is going on here in the second part of the statement is saying that